So the topic for today is going to be the vulnerability research, right? So first of all, who I am, my name is Khalilov Mohammed. Everybody calls me Mo, but majority of the people at work calls me Khalilov by surname because I was from Soviet times and people call by surnames. I'm also the author of about 30 plus 0 days, ranging from the thin client application to thick client, Linux, browsers, and so on and so forth. Currently, I am head of the Red Teamers, and I have got a small research lab where we concentrate on the vulnerability research, hunting for CVEs, and so on and so forth. I don't use a lot of social media accounts, so I got a Twitter, which I check only once a month. So I'm not going to be stuck there quite often. And I also maintain, I got my repository on GitHub where I develop the tools and place them there. Now, what's going to be the agenda for today, right? Agenda for today is going to be the vulnerability research on the thick client applications, specifically on the open source applications developed on C, C++, and so on and so forth. But majority of it is going to be the open source and based on Linux. But it also can be applied to the Windows-based open source applications. But right now, we're going to look at only the kind of a white box, gray box approach, where we have got the access to the source code. You can also apply the same techniques for the black box. Now, on the agenda, we're going to look at what the common questions during the for the fuzzing, for finding the vulnerabilities, where to start, right? And then we're going to look at the life cycle of the vulnerability research and development, where it starts, where it ends, and why we're going to need fuzzing. And we're going to look at the type of fuzzing, right? There are a variety of ways to do the fuzzing. And then we're going to try to understand the instrumentation. So instrumentation is basically a way to applying small set of functions which mutate that function call. We're going to look at the some of the common languages which we try to break and find the vulnerability in, like GCC, like our C programming language, right? C++ and C-lang. So it's basically C, C++, and G and some C-lang. Then we're gonna look at, we're gonna use mainly the American fuzzing law for the fuzzing purpose. And then we're gonna try to understand what's AFL and understand its layout. And then we're gonna look at how we can find the right targets to fuzz, where we should actually search for the right application where we can target to find the vulnerability and find the 0 days there. We're gonna look at how we can optimize and configure our tool, which is AFL. Then we're gonna look at how to create the environment, how we can create the corpus and optimize it. We're going to look at the, maybe right now corpus might be a bit not clear, but corpus is basically what kind of data we're going to feed into the application. We're going to look at afterwards triaging the bug. If you find the bugs, how we can actually triage it, try to find where the vulnerability did occur in the actual application which we are trying to find the vulnerability in. Then we might not be able to write the exploit at this stage, but we're going to try to identify where the issue exists and then what kind of issue it is, and hopefully trying to find what needs to be done to mitigate this kind of vulnerability. Okay, so common questions, right? How to choose a target. So the target is basically what you want to actually assess, where you want to fuzz. So one of the common targets is that the target which should be able to parse some sort of content, represent some sort of data back into the user. It should have quite a lot of functionalities to play with, right? The bigger the scope, bigger the function calls, bigger the functionalities and features, the better for us, because we're going to have the multiple ways to interact with the application. So this kind of applications are really good. And on top of that, the applications, the libraries which are old, is also good for us because there's more chances that they're not actually patched up. Like, I don't know, three years ago or so, there was a vulnerability on Heartbleed, right? It was basically the overflow on the memory, which actually led to expose some of the information from the adjacent memory addresses on the heap. So nobody actually looked at it, but with the proper fuzzing, with the right timing, with the right approach, this vulnerability was discovered. So one of the things I would say is that try to find the vulnerabilities which are a bit old, which has got a bigger scope, bigger function calls, and so on and so forth. And then obviously, once we identify the target, we need to try to find how to interact with this application, what kind of files it needs to actually function properly. For example, if it's going to be the PCAP network file packets, right? Parsing applications like TCP dump, Wireshark, some libpcap libraries through Python, right? We need to understand what kind of files they parse and what kind of format they need to be. So we need to actually understand them. It's not always a PCAP. Sometimes it could be, for example, FFmpeg, right? It's going to accept multiple type of media content and convert them to some different format or modify them. So we need to understand what kind of files we can parse to them. So then another question is that what's the best way to mutate the files and feed into the fuzzer? So there are different type of mutation, right, for the files. There's a dump mutation, there's a very well structured mutation, right? You can actually feed into the application any kind of file, and the mutation will take care of the rest, because it's going to actually change the content, adding the bytes, mutating the bytes, and applying some sort of different algorithms. There are new kind of algorithms coming out every now and then, but having the right file, having the right structured file, and applying the right mutation to the file is going to give you a quicker right result, a quicker bugs. So that's very important. Now, how to detect the real crash and bugs? We're going to look at the example, because during the fuzzing, right, you're going to have thousands of outputs, but going through all of them is going to be very tedious. One of the things is that for you to actually start automating it, trying to find a way how you can parse the large amount of sometimes useless files into something useful and base your analysis on this filtered bugs only. So we're gonna look at this as well in the example. And then sometimes we have got complex applications where we need to provide some different libraries. Obviously, for them, we need to find a way to write a wrapper. Wrapper is basically writing your own code, which would call that application indirectly. So that's something also we're going to look at, provided we have got enough time. We have got only about 50 minutes, so we'll try to make it as fast as possible. So that's what we're going to look in this course, in this topic. Now, now, life cycle of the research is basically going to start with target selection, as we discussed, right? Once we identify the target, let's take an example of the TCP dump. But in this real-life example, I'm going to show you the vulnerability I found on Perl. But I'm not going to go and fuzz the Perl right now, because it's a big application. It's written in C. It's an interpreted language. But we're going to look at, as an example, we're going to take the TCP dump. And then obviously it has got the libpcap, which you utilize as a library. Now let's say you found the target, which is TCP dump. Then we need to understand as a reconnaissance how this application operates, right? It doesn't have to be the TCP dump. It could be any other application, but you need to understand what application you're trying to find the 0-day in. You need to understand how this application works, what kind of features, functionalities, what kind of libraries it's calling to. Then you need to actually start enumerating on what kind of flags it has got, right? For example, sometimes it's got optimization features, sometimes it's got add-on features to call different libraries, which is not by default enabled, right? So you need to look at the help of this application. Normally, when you do the config help, it's going to tell you what kind of features, functionalities it has got, understand it, and then you can start implementing them, embedding them, and including them as part of the compilation process. Then we need to obviously try to understand the interface selection. Now we have the understanding what kind of modules, features, functionalities it has. Then for a better purpose, we need to try to limit our function calls, limit our features, saying that, okay, I want to fuzz a specific function or specific feature of the application. Let's say on the TCP dump, you might be only trying to see, okay, this application is parsing the PCAP file and printing it out back to the user. Let's go and parse that one. So we can concentrate on that one. You need to select specific functions sometimes and go through the fuzzing process on that one. Now, once you have identified what you want to fuzz, then you're going to start creating the corpus. Corpus is basically the file which you're going to feed into the application. Normally, it doesn't have to be only one file. It can be even empty file. The fuzzing process is going to generate the file for you, but till it finds this magic number on the header of the file, it takes ages. It's better that you're going to find the already available file. For example, on the network packet captures on Wireshark, there are a lot of sample PCAP files which you can download, and then trying to find the right file to feed into this application. So that's going to be your corpus. Then obviously comes the fuzzing part. One of the major and most important part is that all of the parts are important, but fuzzing part is where you're actually going to be stuck for weeks, maybe even longer. In the fuzzing, you need to, if you have got the better performance PC or servers you have, it's going to be time saving. You might, for example, in my environment, I have got 12 servers, which I mark one of the servers as a master fuzzer, and 11 servers is going to be it's called right now slave fuzzers, right? All of them is going to communicate with the master fuzzer. So you're going to distribute the fuzz into multiple processes. You can also, in one PC, you can have 16 CPUs. In this case, you can say, I want to use one CPU as a master fuzzer and the rest of the 10, 11 CPUs as a slave fuzzers, which is going to communicate with the main fuzzer to interchange the already queued corpuses, already found bugs, and place them in one place. And once you fuzz it, and let's say after 2 weeks, you come back and then platform the application which you're fuzzing, it says, hey, I found 1,000 crashes. Then you can say, okay, should I stop? Should I not stop? It's up to you, because fuzzing is not going to stop on its own. It's going to carry on forever. So you got to make the best judgment for yourself, saying that, okay, 2 weeks passed, let me stop, let me look at the crashes and trying to find if any of those crashes are usable, right? That's where your triaging comes in, trying to identify, going through the thousands of files and identify which of these files are going to actually cause a legitimate crash, which are exploitable. Once you identify this file, you're going to go and try to find out and which segment of the source code which you're fuzzing is causing this kind of a bug. And then you try to find out that line of code on the application which is causing this vulnerability. That's where your triaging is. Once you actually identify the issue, identify which line of code, what kind of function is causing this crash, what kind of vulnerability it's actually exposing to, then you're going to start writing the report for that specific vulnerability. It's so that you can provide to the to the vendor who is actually developing this application, or to write entities. For example, if you want to have a CVE, you can go to Meter, so some other places where they can assign the CVEs. Now, exploitation part comes later. It's a completely different ball game, right? So fuzzing is one thing, but actually exploiting the vulnerability is completely a different thing. For example, if it's going to be the heap exploitation, it's a different process. It's different than fuzzing. So we might not be able to go that far right now, but we might actually go and find the crash and try to crash the application outside the fuzzing process. Just let me check if everything is working. Okay, so as already highlighted, a reconnaissance stage is that understanding the application purpose. You need to try to understand the application pass and fail behavior of the application. On Linux systems, right, when you execute the application, the process always kind of responds whether it's a successful execution or not successful execution. There's a different type of statuses it has got. Once you understand the pass and fail behavior of the application, for example, if you're going to pass, let's say, network packet into the media application, is going to say, hey, it's not the application, it's not kind of a file type which I handle, and it's going to give you the error message. Then you might be wasting your time. Maybe you're providing incorrect input. Maybe it's trying to parse it, but it's giving you the completely unexpected behavior, which is going to be useless for you. Then you need to understand the flags and the functionalities, right? What kind of features you can actually perform with this kind of application, what kind of, for example, TAR has got archiving tool on Linux. It has got many other ways to archive the application with different algorithms, with different compression algorithms. You need to understand them, and you try to see which one of them you want to actually go and fuzz. One of the best ways is that is reading through the manual or going through the help section of that specific application developed by the vendor or third party. Once you actually understand it, you can start selecting the correct test cases for those parameters. Finding the right corpuses, right files is very important during the fuzzing. It's gonna give you a smart way to fuzz the application. So as I said, one of the best ways, the screen is quite small, I know, but you got the idea. You can go with help or man functionalities of the Linux, or help or README file. Go through this, understand the flags, understand the features, what's the main purpose of the application. Based on this, you're gonna draft and your development process for this fuzzing. So I'm just going to skip some of it, right? But the test cases could be file types. It could be the network-based values. It could be the user input from the files. It could be through the parameters, right? So, for example, FFmpeg, it could be the file name, or maybe, let's say, ID sudo function. For example, Linux sudo will have some flags with some user inputs, right? So there are different types of to interact with the applications. That's also you need to identify. So as I said, one of the best ways is that for you to find the right file. For example, here you can have a file type downloaded from the available captures. For example, here is from the Wireshark. There are tons of file capture samples. You can download them, save them, and let's say you downloaded hundreds of files. And then we're going to look at how we can select the right test cases later in the slides. And then let's say you have got the input files which the application accepting. Let's say sudo application, right? I think last year or the year before, there was a vulnerability on the sudo, because sudo accepts the user inputs. And in this kind of test case scenarios, you don't have to have a file directly inputted into the, it's not parsing the file, it's taking the user input, let's say, and then taking actions based on this. In this kind of scenarios, what you need to do is that you need to identify what kind of the inputs from the user is the application is expecting. In this case, how you create the file test cases is that you're going to create correct test cases as a file. For example, test case 1 could be, let's say, file name 1 could be John Doe, and then second parameter could be correct strong password. And then second test case would be John Doe and incorrect strong password. And then so that the AFL or any kind of fuzzing is going to understand what kind of use cases and what kind of functions it's actually testing. Application, if you look at it, right, it's got a condition. if the username is correct, okay, take me to the next test case, is the password is correct. Then, if the password is correct, execute this function. So you see the flow of the execution is going through the different process. Now, if the application username is correct, but the password is checked, right? And then it's hitting that condition saying that password is incorrect, and it's going to take you to different function. So now we're calling the different function to fuzz as well. So having the different variation of test cases is very important as well, so that you're going to trigger the right calls, and then you can start fuzzing those specific calls as well. Now, the fuzzing, obviously, how it starts is that it's going to start executing it, it's going to test the cases, and then it's going to execute the program. If there's no violation of the program, right, like let's say Stack Overflow or heap overflow, what happens is that in the fuzzing, there's a queue of pre-mutated test cases, and then it's going to go back and take a different type of test case and execute the program again and again till it finds the violation of the program execution. So when you execute the fuzzing, what's going to happen is that obviously you're executing the program, but for this program to be executed, you need the test cases. The test cases which you generated is going to be a key role to create multiple thousands of pre-mutated by the application test cases. And then the process is going to carry on till the application finds the right file which is mutated in such a way is going to crash the application. Once the application violation is determined, then it's going to consider this as a bug, and then for example, AFL is going to place it in a folder called crashes. And that's going to be your main target to observe during the analysis stage. So fuzzing is not going to be able to find you always a good bugs. If you want to actually find the very excellent bugs, it's very fast. It can be smart. It can be calculated, right, based on what kind of corpuses you select. It can be very well automated, but it might also going to miss a very good bug, which is not going to be able to detect through the fuzzing. Because for that kind of logical bugs, you need to analyze the source code. You need to analyze how specific functions are triggered, which are not easily reachable by the automation. So it's one of the drawbacks of the fuzzing. But fuzzing is always a good way to start the software security, making sure that it's functioning as it should be. So fuzzing, what kind of bugs it can find? It can find heap overflow, right? It can find the integer overflow, stack overflows. You're not going to always find nowadays stack overflow because a lot of the compilers are taking care of this, but it doesn't mean it's not there. A lot of the time, heap overflow is there, null dereference is there, use after free vulnerability is there. But for example, format string, it's there, but you're not going to always find the stack overflow or format string overflow. I'm not saying it's not there, but majority of the time you're going to find the vulnerabilities on use after free, null dereference, risk conditioning, and integer overflow. Now, if you want further, after fuzzing, if you want to go to the exploitation stage, each of these attack vectors, for example, for use after free, double use after free, null dereferencing, there are different techniques for the exploitation. So you might as well spend your time understanding those kind of exploitation. Stack Overflow is good. It's easy to understand. You might as well cover this. And heap overflow is also excellent. But if you want to understand and exploit the vulnerabilities, try to spend more time on the use after free, integer overflow, null dereference exploitations. Null dereference, I start to see a lot on the kernel exploits. I found, I think, about 4 vulnerabilities CV assigned on null dereference and quite a lot on the use after free vulnerabilities. So briefly, I did discuss about the type of fuzzing. So there are kind of a dumb fuzzing, smart fuzzing. So it depends on how you're going to provide the files. It's basically generating the input with no structure, right? It's a kind of a dumb fuzzing, but providing is with the type of file which is expected by an application is kind of a smart fuzzing. And there are different type of mutation algorithms is embedded into the fuzzers nowadays. It's going to go through different type of mutations as it rotates fuzzing with predefined algorithm. So that's a key role. What kind of flags are you using during the fuzzing? So I put here black box fuzzing. It's black box fuzzing is that when you don't have a source code and you're not able to instrument the application. But that's the way with the AFL, which is providing the KMU-based, virtualized-based fuzzing of the application, which you don't need the source code. It's basically going to go through the file, mutate it, and then fuzz the application, parsing it into the application. I'm just going to skip some of this part, right, because we don't have a lot of time, because I want to show you some of the demonstrations as well. It's basically what I said, but a bit more in a pretty written format. So function coverage, I just gave you an example of the input field, for example, for sudo or password input field, right? So it's basically what kind of file, what kind of content you're providing to the application. It's going to make a call to different function based on the return from the test from that call, based on this if else conditions, based on the jumps, based on the based on the response from the application. So I already told you about the AFL, so I'm just gonna skip this part because I want to concentrate more on the practical approach, or once I jump into the console. So I already explained to you about the AFL algorithm, right? It's just gonna take the test case, put it in the queue, and then it goes through the queue, iterate it, and if it finds the application, which is if it finds the corpus which is crashing the application, and it's going to put it into the crash folder. But if it finds an interesting file which maybe did hang the application but didn't crash it, it's going to put it back into the queue, or it's going to use it as another mutation for the next test cases. And so the fuzzing is going to create thousands of files in a second, or maybe it's going to iterate, so it's going to be quite heavy on your hard drive. So we're going to look at the optimization soon, but it's basically quite a lot of read and write on your hard drive. So I'm just going to I'm going to tell a little bit, but not a lot. There are different type of compilers. It's basically it's going to be the assembly language, which is low-level interaction with the CPU, but the fuzzing is going to be embedded on the function calls. And then every time when the function call is executed on the application, this instrumentation, AFL instrumentation, is going to be there before the function call and understand how it's responding on the return from the function call. You know that on the assembly, every time when you make a call, it's going to create this region on the EBP to return to the previously called segment of the application once the function call is executed. When the return is coming back with the invalid value, this instrumented function is going to check if it's a correct value or not, and then AFL makes its decision based on this. So I'm just going to skip this sample code, like how the GCC is going to look like for the same application. For example, on the C programming language, it's quite simple. The same applies for the C++. Right, but on the assembly, it's going to be quite, you know, a bit more. No, I don't think a lot of people write in assembly anymore, including myself. Out of interest, I did write a few times, but it's not something that we'll write a lot. But at the end of the day, anything which is compiled is going to be into the assembly language. So this is something that I already told you about the instrumentation, where it's going to inject the piece of code before each of the function call to jump, and then go through the return value, see if it determines crash or not. Now here, I don't know if I can zoom in, but here, as you can see, for each of the call function is actually placing its AFL is placing its trampoline jump function call, right? Saying that, okay, for this call, I want to, for each of the calls, is AFL is instrumenting and it's placing its value, saying that let's see what's going to be the return value of this application. But if you did compile the application without instrumentation, it would haven't put this kind of function call. Now, AFL, the look and feel is going to be something like this. It's pretty much always like this. So at the top, you're going to have the, your application target, right, which you're trying to fuzz. And here is the overall results, how many passes it has taken. Pass is basically how many function calls, how many function calls it's basically it's made, how many interfaces it managed to interact, right? And which is going to go through and increase a lot as the application is going to mutate the corpus. It might be able to find different function calls to make. So here we got to pay attention quite a lot on the unique crashes. It might have found quite a lot of crashes, but this is something that we need to concentrate on. Unique crashes right now, it managed to find about 14 unique crashes, but we don't normally stop on this kind of unique crashes when it's 14. It's better that we stop when it's over 100 or over 200, and we give it a time at least like 4 days, 5 days, which I normally do. And another thing that important part you need to pay attention is that execution speed. Right now we're executing 1,343 executions a second, but that's going to be a key role when you define the right corpus into the application. Not only the corpus, not only the file, but it also plays role your CPU and your storage. SSD is much faster, and HDD is not really suitable always for the fuzzing, but it's cheaper, right? Because fuzzing is going to create, as I said, a lot of queue files. So it's going to go quite big. So you might as well have enough space on your hard drive for that. So here, as I said, it found like 2,000 crashes, but out of them uniquely 14 crashes. So here we're mainly talking about the mutation, what stage of the arithmetics we're looking at, right? What kind of flips it's doing, and what kind of mutations. So that's something that I would suggest right now is going through the Havoc mutation, but I would mainly suggest that you concentrate on the execution speed and the type of unique count of crashes, as well as how many passes it found. Let's say you're providing the input file TCP dump. It's a big application. If you got a total pass of only one for 1 day, it means that there's something wrong with your application corpus that you need to revisit and then apply the right corpus for this one. It normally should increase quite big time. I think I'm running low on the time. So what's hunting for the target, right? Where we normally hunt for the target. I normally search Linux itself for all the applications, right? I normally use apt-cache search, and I put a keyword. For example, if I want to go and find a vulnerability on XML parser or converters, right, which is quite easy, I use apt-cache search converter or apt-cache search media or parser. And then it's going to give me the list of all the application which deals with the parsing, which deal with the compression, which deal with some other kind of keywords which I'm interested in. And then I'm going to take the specific application or library and find the newest version online or from the GitHub repository and use that application as my target. You can also use a Softpedia. You can filter down to Linux operating systems, specifically on the command line prompt. On the GitHub, you can also filter down to specific applications and choose the right application which has got quite a lot of people who is using it, quite a lot of applications which are using it, and concentrate on them, because you also want to show the impact of your vulnerability, right? If you find a vulnerability on some application which nobody's using it, it might not be interested for it. It might not be very interesting. So you might as well find the right application. but with the least attention by the developers. GNU project got quite a lot of applications. Obviously, as an open source, you can go to the GNU project and download some of the files. For example, you can download the tar file, which I did, I think, a few months back, and start fuzzing on it, right? And it's easy because you can create quite a lot of different type of archiving formats and try to attempt fuzzing it during the extraction of those files. You can use a Google Doc, and Google Doc you can use, for example, you can find latest application on C or trial versions of some of the application, and find the ones which are not quite well tested by the developers or by the community. So AFL installation is quite straightforward, right? First of all, your Linux system got to be updated. You need to install the essential tools, build essential, CLang, GCC, and the GNOME debugger. And then you go and download the AFL from the from this website. You can download from GitHub as well. And then once you download it, extract it, and then you just run the configure, make it, and make it install. You can you don't have to go always make it install, right? But if you do sudo make install, it's going to be always available in your environmental variable on your Linux system. You can enable the optimization for the LVM, for your CLang, for some of the application, if you want to, if they accept the LVM, if they accept the CLang, like OpenSSL, if you want to go faster, you can use this mode. But normally when you go with the LLVM, you got to have a much better RAM. It's better if you go in for the big application. I suggest to go with a bigger RAM. Once you install it, one of the key things that you need to do is that you got to make sure that the core pattern is enabled, so that you got to see the crashes on the applications, so that it's dumped on the file. It's not dumped in the log file only. Then there are some tools which is going to help you to perform the debugging process, but this should be enough to install your application for fuzzing. As I said before configuration, what I normally do is that I go with the configure, try to understand the application, and see what I can enable, what I can disable, and then use those flags to compile with the instrumentation. If it's okay, I'm just going to go to the console, and just maybe I'll show you there instead, so I can show you the optimization as well. So this, sorry, this is some of my servers. So let me try to go to one of my servers. So this one I will come back. So before I run TCP dump, I'm sure that's a config file, right? What I normally do is that, as I mentioned, let's say we did download the config TCP dump, but which we try to understand what it does. We know that it has got quite a lot of features, functionalities, and sometimes if you want to fuzz it efficiently, you might want to enable some of the critical features which are not tested. If I want to enable everything, what I do, I just use some grabbing to take some of these values. No, I don't know if you can see it or not. Maybe, for example, I have got here only SMB. Let's say we have got 10 features which you want to enable. That's something for you. I'm telling you for optimization purpose. Let's say I'm going to put here flags. .txt enable SMB. Now, before I start doing the instrumenting it, I normally go with first I'm going to define during the instrumentation, instead of using the built-in C compilers, I'm using the AFL GCC, and then I'm using the, instead of C++, I'm using the AFL G++, which is for your C++. Then I'm enabling some of the C flags. And C flags is basically any the flags which says, okay, during the compilation, do you want me to optimize it? Do you want me to enable the extra debugging? So it doesn't always have to be for the AFL, but for in general, we would normally enable these features for troubleshooting and maintenance purposes. And then I'm going to go with configure, and then I go this I don't know, it's asterisk, right? And then I'm going to say cat, and then I said flags.txt. Now, what it does is that instead of going through on the configure, enable SMB, blah, 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 and go all the way down here, you can go and grep out all the enable or specific features you want to parse, and then you're going to go and execute it this way. And then, because I did compile this one already, I believe. Yeah. I did it compiled already. So once you enable this and then compile it, it's going to be already here. One of the things that I want to say is that during the compilation of one specific program, there's sometimes it's a library which is missing. In TCP dump, there's a libpcap, which is one of the important libraries which TCP dump uses. What I normally do is that I also fuzz the instruments, the libraries also, so that it's going to be easier for me to fuzz the libraries at the same time. I don't think, I didn't instrument the library right now, but anyway, I did instrument the libraries. It's there, and then if it's library, I normally make sure that I also put it as environmentally accessible for the TCP dump. Okay, great. Now it's there. Let's say now we go to TCP dump. Now we're ready to go and try to fuzz this application. Let's see where it is. Now we're fuzzing the TCP. We're instrumenting the TCP dump with the AFL fuzz. Now it's working. Let it go and instrument this application. It's basically compiling the TCP dump with the AFL fuzz function calls, which try to find when the crash occurs. It's going to tell me, okay, there's a crash. I want you to correct it. Okay, great. Now it did work. Here I have got a small file called iperf, and this is one of the pcap files which I did download before. Before you fuzz it, one of the things that you need to do is that you need to install the, you need to create a directory called input and then directory called output. Okay, so what happens in the input file is going to be your corpuses, and the output file is going to be the any file which AFL fuzz as a crash is going to place it in there. Now, what we're going to do is that TCP dump is our subject application, and we're trying to actually run this command called TCP dump. Let's try to make sure that the application is working properly, and then we're going to give it file name called iperf. Let's say make sure that application is working properly. We're not fuzzing anything. Okay, it's reading the file, everything's working. Now what we do is that we're going to try to fuzz it. For that, what we run AFL fuzz, and then input. We're going to give it our input file where our corpuses is, and then we're going to provide the output file where we want the output file to be. And sometimes I'm going to tell you in a bit. And then instead of providing the actual input and folder and the file name, we're going to give it at sign. What it means is that instead of at sign, take the file from the input as a corpus and then put it as a main interactive file to go through. Now, as you can see, what it's doing is that it's taking this one specific file and then going through this through multiple type of algorithm. Right now, it's going through the havoc, it's going through splice, and assigning different mutation and trying to find the bug. And its execution right now is at 723, 730 kind of executions per second. It did crash. It's going to take some time. Now we have seen how the AFL fuzzing is working and executing it. I'm sorry I'm being a bit fast, but let me try to be as fast as possible. Right now I'm executing with only one CPU. But if you have got, for example, in my case, I have got 12 CPU, and as I said, you can run the AFL with master-slave mode. And let's say you have got multiple CPUs. What you can do is that you can say -m fuzzer1. It's going to be your master fuzzer, right? And then let me put it on the screen. Fuzzer1. Let it go to the background. Screen. I don't think I have got the screen installed. Just a moment. Yeah, I don't have the screen installed. Now, you can have multiple fuzz to be run in parallel. In my case, I can run 12 fuzzing machines at the same time. But what I have to do is that for the first one, I can use master fuzzer, and then for the rest, I can do slave fuzzer as 1, 2, 3, up to 11, right? So I can go and fuzz multiple in multiple CPUs so that my process of fuzzing is going to be faster and faster. Now I'm just while we have time, I'm going to show you one of the triaging parts. Before I run out, I want to make sure that I'll show you this one so that you're not going to go without actually seeing the proof of concept of anything. So one of the exploits, what I did for I did find for the Perl. Let's say you found a crash, you got the corpus, you did analyze it, and you found which way it's actually causing the crash. What you do is that you got to run the application outside the fuzz, pass this crashed corpus, which is your file. In my case, it generated the AFL generates a file called ID or whatever, and some numeric value. And then you open your, for example, in my case, it was Perl. I did open the Perl in GDB, and I parse this file name into this application, into the Perl. And then what GDB did is that with PIDA, it actually told me, okay, it's calling the libraries, Linux libc calls, and it's saying that, okay, the actual crash happened on the specific memory address. Now you might say, okay, where does this memory address come from? If you remember when we're fuzzing, we said, okay, enable the GDB, right? It's a greater debugging feature. And with this information, with a specific address, what I do is that I go and try to see, okay, this specific address, I take it and I place it into something called ADD to line. So ADD to line, what it does is that it's going to go and check the virtual memory address of this specific application, and on this address, what type of line of code is lying. So here, I'm putting the same address. I'm giving the Perl name, my executable, and it has got a virtual memory address, and that on the specific memory address, I want to know what kind of source code is lying. It says on the specific memory address, it's called under the Perl utility C, and on on line number 402. Now, if you look at it, on line number 402, we realize it's basically a memory corruption. Heap overflow is happening here. So here we're actually saying that, okay, here we're freeing the memory, but we didn't actually assign anything on this region before. That's why we're freeing the memory without assigning anything. So this is basically called the double free vulnerability. Now, let's see if I'm right on time. I know this is very short time to go through this. You know, it's quite a lot of things to talk in 50 minutes, but I try to do my best. But one of the things that I want to show you, and before I leave on, is some of the notes, right? as we all try to be, you know, hackers or security researchers, right? One of the things we do is that we try to automate it. Make sure that when you're fuzzing, you're trying to use the SSD, which is going to be much faster read and write process. Enables the debugging feature, so it's going to help you to actually get the virtual memory address, and then enables the fsanitize address. It's going to try to find you the heap corruption vulnerabilities, and then try to, since we don't have a lot of time, it's going to run for weeks and days, try to actually automate the process of crashes. I normally, when I put my AFL fuzz, I write the bash script. It's going to take the output and put into my Slack channel. So if there's a crash, I'm going to notification on my phone saying that, hey, there's a crash happened, and then it's going to go to my Slack API. I try to actually also manage my disk space with a cron job to erase some of the unnecessary queue files. Okay, so this is a quite fast-paced approach. It's quite a lot of things to talk about, but I wish we had more time.